Welcome to this lecture on classification in machine learning. I am Dr. Andrei Holz, and today we'll explore one of the basic tasks in machine learning, classification. It's a powerful tool that is used in many fields such as finance, medicine, engineering, anti-fraud. Let us move on. Today we'll be talking about the fundamentals of classification, exploring key concepts, models, evaluation techniques, and challenges in classification tasks. We'll start with the basics of classification and discuss why it is important for solving real-world tasks from spam detection to customer segmentation. We'll discuss this during the classification problem-solving setting. Then we'll dive into the models of classification. It will be K-nearest neighbors, decision tree classifier, logistic regression, and we'll take a look, just an overview of the support vector classifier and naive bias. We'll then move to the metrics like accuracy, precision, recall, ROC, AUC to evaluate model performance and discuss validation techniques to ensure models generalize well. Then we'll address common issues and challenges in classification, such as class imbalance, high-dimensional data, and interpretability, and strategies to manage these challenges. Finally, we will review the main takeaways, reinforcing critical concepts, the strengths of different models, and practical tips for classification tasks. By the end, you will have a foundation in classification and understanding of essential models and tools to handle common challenges. Before diving into classification, it is important to understand where it fits in the broader context of the CRISP-BM process, like the standard of data science. Actually, it is not a big deal. We're still in the modeling phase, as with the regression. Our aim here to extract meaningful relationship from the data by creating a model. So let's talk a little bit about the classification. Classification assigns labels or categories that's a target to new observations based on historical data patterns, features, and that is a supervised machine learning problem. Since we do have labels, we do have targets. Some examples, let's say spam detection, so it's like binary. Is it spam or not spam? Image recognition, so what is on the image, and we have like several classes. Is it a cat? Is it a dog? Is it a cake? Is it a bat? Disease diagnosis, so we might need to estimate which disease is present, like in, and anti-fraud binary 0-1, binary highly imbalanced. So, and what types of classifications do we have? So we have binary, as I mentioned, it's like only two outputs. Multiclass, we have more than two categories, something like a cat, a dog, a fish. Multilabel. Labels can apply simultaneously, just like in Instagram tags or something like this. And ordinal categories here have a natural order. So it's 1, 2, 3, and 1, 2, 3 is meaningful. It's not just numbers. At its core, the classification problem involves finding an approximation for the relationship between our features and target variable. We represent this relationship as y equals f of x. Y is the corresponding class label from a set of k possible classes. It is that simple. We are dealing with the discrete class labels in classification, not continuous variables. And as you can see here, so our classifier divided one class into this area and another class into that area, like the orange one and the top orange one and the bottom blue one, and our classifier divided this by a line. There are various types of classifications models we can use. Let us review some of them. KNN, or K-nearest neighbors, is one of the simplest yet powerful machine learning algorithms. It does not require an explicit training phase, and it uses the entire dataset to make predictions. This simplicity is one of the reasons it's often chosen as a straightforward point for classification tasks. KNN classifies a point by majority voting among its k nearest neighbors. Mathematically, this involves selecting the class that appears most frequently within the neighborhood of the new point. Weighted KNN enhances the standard approach by factoring in the distance of each neighbor. This weighting scheme reduces the impact of distant neighbors, leading to more accurate and reliable classifications, especially in diverse data landscape. Distance metrics are central to KNN. While Euclidean distance is the most frequent one, alternatives like Manhattan and cosine distances are chosen based on data characteristics. The choice of metric significantly influences KNN performance. For instance, cosine distance might be a good choice if you're dealing with the high-dimensional data or with embeddings. KNN prediction phase scales linearly, while the number of data points and features making it computationally intensive for large dataset. Optimization methods like KD trees and ANN can significantly reduce this problem. In high-dimensional space, distances between data points become uniform, reducing KNN's ability to find meaningful nearest neighbors. This phenomenon, known as the curse of dimensionality, poses significant challenge for KNN effectiveness. Let's take a look at KNN for classification in practice. Today, we're going to work through a hands-on session using the K-nearest neighbors classifier. We'll be using the breast cancer dataset from scikit-learn, which is a well-known dataset for binary classification. The practical lecture will guide you step by step through implementing a KNN model, understanding its nuances, and exploring advanced variations to achieve optimal results. Let's dive right in. We start with imports, as usual. Let us import everything that we need. Basically, we need pandas, we need matplotlib, we need scikit-learn, and we need the dataset. So the dataset, as I said, it's breast cancer dataset, is loaded with scikit-learn's load breast cancer. This dataset consists of several numerical features relevant to diagnosis tumor. The dataset includes 30 features, numerical features that describe characteristics of cell nuclei present in breast tissue samples. The target variable has two classes, malignant, represented as 0, and benign, represented as 1. This makes it straightforward binary classification problem suitable for illustrating the strengths and weaknesses of the KNN. Let us check the distribution also here. Yeah, it is relatively balanced, so we won't be using any imbalance techniques. And yeah, data preparation. So proper data preparation is crucial for KNN since it relies on distance metrics to identify neighbors. Unlike decision trees, KNN is highly sensitive to the scale of the data, and therefore it is important to standardize the features to ensure that each feature contributes equally to the distance calculations. As you can see, we scaled it. We split the data into train and test using like the standard rule, and we scaled everything. We split the dataset into training and testing sets using 80-20 ratio. This ensures we can test our model on unseen data. And using standard scaler, we scale the features to have zero mean and unit variance, which is critical for KNN to function effectively. Without scaling, features with large values like radius will dominate distance calculations, leading to biased neighbor selection. Standardizing ensures that all features are on the same scale, which allows the distance metric, usually Euclidean, to treat all features equally. We start by training a basic KNN classifier with default number of neighbors. Yeah, the default number of neighbors, if I remember correctly, is 5. Yep, neighbors 5. So let us see what is the accuracy of this classifier out of the box. So it's like 0.96 or 96%. So model training. The model is trained on the standardized training set, and predictions are made on the test set, and accuracy is calculated However, it is important to remember that accuracy alone does not tell you the whole story, especially in medical datasets where false negatives are extremely costly. Let's take a look at the confusion metrics. We use these tools to understand the situation, the model performance in detail, identifying how well it predicts zeros and ones. The confusion matrix is plotted to provide a visual representations of true positives, true negatives, and false negatives, which is helpful in understanding model errors. The classification report provides precision recall F1 score for each class. So precision measures how many of the predicted positive cases are actually positive. Recall or sensitivity measures how many of the actual positive cases were correctly predicted by the model. F1 score is the harmonic mean of precision and recall, providing a balanced metric when dealing with imbalanced classes. So we have our estimations now. Let's take a look at the hyperparameter tuning. To improve performance, we perform hyperparameter tuning using grid search cross-validation. Have this classifier and our grid. Well, let's try to find the optimal number of neighbors, or the K. Cross-validation helps in ensuring that the model's performance is consistent across different subsets of the data. Let's take a look here. Yeah, optimal number of neighbors is 8, and we'll have a better accuracy with this number. So once the best K is found, we retrain the model and observe improved performance. The choice of K plays a critical role in the bias variance trade-off. A smaller K results in a more flexible model with lower bias but higher variance, which may lead to overfitting. A larger K results in smoother decision boundary with higher bias but lower variance, which may lead to underfitting. Let's take a look at our cross-validation score. Yes, so the cross-validation score is stable. We even try to stratify this whole thing just to take a look whether stratification makes sense in our case. Well, as I mentioned, since we do not have like high imbalance, we can use stratified split or not use, so it is not making a drastic change here. Let us explore advanced variations of K and N to enhance the performance. The first one is weighted K and N. In standard KNN, each neighbor contributes equally to the final prediction. With weighted KNN, neighbors are closer. With weighted KNN, neighbors that are closer have higher influence. This can sometimes improve model accuracy, especially when the class distribution is not uniform in the neighborhood. This approach is particularly beneficial when some neighbors are significantly closer than others. Let's take a look. Yeah, and we still have like weighted accuracy the same, so nothing changed. We can also have different metrics, different distance metrics. Let's use Euclidean and Manhattan distance metric. What is a Euclidean distance metric? It's the most common distance metric, which calculates the straight line distance between points in a multidimensional space. Manhattan distance, also known as L1 distance, this metric calculates the distance by summing the absolute differences of the feature values. This can be more appropriate when dealing with features that are not smooth or when dealing with high dimensional data. And as we can see here, with Manhattan, distance accuracy is a bit lower. And yeah, we can compare everything. So, well, standard and weighted perform the same for us. And with Manhattan distance, it's a bit worse. So we'll stay either with standard or with weighted. And such things help us understand the impact of different distance metrics and schemes, weighting schemes on model performance. Let's move further. Okay, further we'll have the model evaluation. We'll skip it for now and discuss it a bit later. Just for the quick overview, we'll be talking about accuracy score, confusion matrix, we talked about it a little bit, estimation of probabilities, yes, KNN can estimate probabilities, receiver operator characteristic curve or ROC curve, interpretation of ROC curve, class score distribution, estimating the thresholds, but we'll talk about it a bit later in the section of model evaluation. However, you'll have this notebook and you'll be able to take a look at the full notebook with implemented model evaluation pipeline. As a conclusion, in this practical session, we explored the K-nearest neighbor classifier using the breast cancer dataset. We covered data loading and pre-processing, model implementation and hyperparameter tuning, finding the optimal number of neighbors, and some advanced variations of this algorithm of the KNN, weighted algorithm and like various distance metrics. KNN is simple yet powerful algorithm that provides a good foundation for understanding more complex machine learning concepts. It emphasized the importance of the data preprocessing, hyperparameter tuning, and the impact of distance metrics on model performance. It highlights the importance of carefully choosing the right evaluation metrics and decision thresholds. Feel free to explore further, experiment with different parameter settings and variations to gain a deeper understanding of the algorithm. And remember that practice is a key to mastering these concepts. And the more you experiment, the more insights you'll gain. Welcome back, and let us continue. Just to remind you what is a decision tree. It contains of several elements. The root node, it's the starting point of the tree at the top, represented by a yellow box here. It represents the initial decision to split point based on a feature. Decision nodes are represented by blue boxes. Decision nodes are points where the trees split based on certain conditions of the data features. Leaf nodes are shown in green and represent the final outcomes or predictions after the decisions are made. No further splits happen beyond leaf nodes. And in general, tree is this kind of structure. It contains of branches that contain nodes that contain leaves, and this is the representation of your data. Another meaningful information is that while we are building the tree, we have impurity levels, and then they can be illustrated how decision nodes aim to create groups with similar class labels. And very impure nodes contain a mixed class, while pure nodes contain instances of single class, ideal for classification accuracy. As in the example at the top here, so when we split the data, we try to have as much instances of the same class after the split as possible. This is the way that we reduce the impurity. A decision tree classifier segments the data by recursively splitting on feature values to create a tree structure. Each split aims to create purity in terms of class labels. The objective is to build a tree where each internal node represents a decision rule on one feature. Branches represent the outcome of those rules, and each leaf node represents a class label. What is a decision rule? At each node, split the data by choosing a feature and threshold that best separate classes according to a defined metric. Gini, impurity, or entropy. Decision trees split data by selecting features and thresholds that maximize purity in child nodes. Gini, impurity, and entropy are common metrics, both favoring splits that best separate classes. Information gain uses entropy reduction to find ideal splits. Training a decision tree involves recursively splitting data, which can be computationally intensive, but scales logarithmically with data. Prediction is efficient due to the tree structure, which allows quick transversal from root to leaf. Decision trees can easily overfit due to excessive splits capturing data noise. Pruning and limiting depth are effective methods to control overfitting and improve generalization for trees. Decision trees are known for their transparency and straightforward interpretation. Each split represents an understandable decision, and the structure itself can be visualized and explained to stakeholders. Additionally, feature importance metrics provide insights into which features matter most, making decision trees a popular choice in high-stake industries requiring justifiable interpretable models. This tree diagram shows the decision-making process at each node. Each split is based on a feature threshold, and each path from the root to a leaf represents a decision rule that determines the class. And the bar here displays the importance of each feature in the decision-making process of the tree. Here, the petal length and the petal width are the most influential features. And we can even take a look at the if-then rules that can be digested from the tree. So if petal length is less than 2.45, then class is TOSA. If it's more than 0.245 and petal width is less than 1.75 and petal length is less than 4.95, then class is versicolor. So, and we can get all the rules from the tree just by running through it. What about the applications and limitations of the decision trees? Well, as for tasks, they are similar to the one that we reviewed before. It's a classification tasks. It's a classification model, so it operates on a various scale. What about applications and limitations of decision trees? As for the applications, they are similar to the one that we recently reviewed. As for the limitations, trees may overfit and will overfit. They are unstable. Small changes in data can lead to different splits. And the trees are biased to axis-aligned boundaries, meaning that they're less effective for data with non-rectangular class separation. So what it means, let me show you. It goes like this. So each time our tree tries to separate this, it should cut this plane, and this is like, it will be really hard for you to find this splitting, having parallel cuts just to get this red and blue separated. Let us take a look at the decision trees for classification. Hi everybody, and we're diving into a practical implementation of a decision tree classifier using the breast cancer dataset. I'll guide you through step by step, highlighting the key procedures for creating a reliable classification model. We will cover data preparation, training, hyperparameter tuning, and evaluation methods to gain a deep understanding of the classification process. Let us focus on this task and move on. First step is imports. Let us import everything that we need. Basically, we'll be using pandas and numpy, scikit-learn, and seaborn. And of course, the data set. Let us load the data set. We need it. And let's take a look at it. Let us check the distribution. It is relatively balanced. There is again no need for any significant techniques to deal with the imbalance. Decision trees do not need feature scaling, which is one of their major benefits. Unlike other algorithms, trees are insensitive to the distribution of the data, meaning we can save time by skipping scaling or normalization. Also, trees are not affected by the correlation of the features, so we can skip the correlation analysis also. We still split the dataset into training and test sets using 80-20 ratio. This split ensures that the model can generalize well on unseen data. So we split the data. Then we try the basic model with default parameters. The model is trained on the training set and evaluated on the test set. The steps are as follows. Accuracy is calculated to provide a basic idea of how well our model performs. However, accuracy alone can be misleading, especially when dealing with imbalanced dataset. Although the breast cancer dataset is relatively balanced, it is always good practice to examine additional metrics. We'll use confusion metrics to visualize the performance of our model in distinguishing between zeros and ones. The confusion matrix provides insights into true positives, true negatives, false positives, and false negatives. Classification report is generated to provide a detailed view of precision recall F1 score for each class. Precision tells us how many of the predicted positive cases were actually positive, while recall tells us how many of the actual positive cases were correctly identified by the model. The F1 score provides the balance between precision and recall. It's a harmonic mean, and it is useful when the cost of false positives and false negatives differs. We can adjust it by the coefficients. To improve model performance, we perform hyperparameter tuning using grid search CV. This technique helps us find the best values for parameters like max depth, mean sample splits, mean sample sleeves, and splitting criteria either Gini or entropy. Let me briefly explain these parameters. Max depth controls the maximum depths of the tree. A deeper tree can model more complex relationships but risks overfitting. Mean sample split, the minimum number of samples required to split an internal node. Increasing this value helps prevent the model from learning overly complex patterns. Mean sample sleeve is the minimum number of samples required to be at a leaf node. This prevents the model from creating nodes that are too specific. Criteria is the function used to measure the quality of a split. Gini, impurity, and entropy are the most commonly used criteria. And using grid search CV, we test different combinations of these parameters to determine which combinations yields the highest cross-validation accuracy. Once the best parameters are found, we retrain our model using these parameters and evaluate its performance again. Typically, we see improvements in metrics like accuracy, precision, and recall when using the tuned model. As we can see, we found the best cross-validation accuracy, and it improved compared to the accuracy with default parameters. Let us retrain the model with these new parameters. It's a bit lower than the estimated here, but let us take a look at the cross-validation scores. It is always good to take a look there. Yes, the mean on cross-validation score is a bit higher, and by the way, for some reason here stratified split helped us a little bit improve, but we need to check whether this is statistically significant change or not. Maybe we're just lucky, or maybe that happened as a weighting scheme, since we applied weights in stratified k-fold. We use stratified k-fold and k-fold cross-validation to further validate the reliability of our model. Cross-validation is an essential technique to ensure that our model isn't just memorizing the training data, but is learning generalizable patterns. In stratified k-fold, the folds are made by preserving the percentage of samples for each class, ensuring balance across all folds. This is particularly important for classification problems, as it ensures that each fold is representative of the overall dataset. Cross-validation provides a more robust measure of model performance by training and testing the model multiple times across different subsets of the dataset. This helps mitigate the variability that might arise from a single train test split. Decision trees are excellent for determining which features are most important for classification. We use the feature importance to evaluate and plot features that are important. This attribute provides a score for each feature, indicating how much it contributes to the decision-making process of the tree. Understanding feature importance helps us gain insight into what drives our model's decision. In our case, it may be certain measurements of the breast tissue, like mean radius, mean texture, that are especially predictive of whether a tumor is benign or malignant. Visualizing this feature's importance using a bar plot helps in quickly identifying the most influential features. Let's take a look at the code. Yes, and we can see that some features are super important. So radius is very, very important. This is interesting. And let's plot the most important features. Yes, the most important are those. And we can also visualize the decision tree. So let's take a look at our decision tree. And this is the decision tree that makes decisions. So as explained, you can go up to the leaf, to the final leaf, and you can even build the if-else rule out of this tree. There are some approaches that are different. We can calculate the permutation score. So it measures the increase in the model's prediction error when a single feature values are randomly shuffled. For this, we can also have this like score. As for the advanced techniques in trees, there is a pruning. To prevent overfitting and improve the generalization of the model, we use pruning techniques. We'll take a look here at the cost complexity pruning or post pruning. It involves calculating the complexity of the tree and eliminating branches that contribute little to reducing the error. This helps create a simpler model that generalizes better to new data. Let's take a look. Yep. This is the graph, the calculation, the total leaf impurity, and we can try to find the optimal value of this. Yes, the test accuracy at optimal value, and let's take a look at the model. Yep, and here we can see the pruned decision tree. Another one is limiting tree depth or pre-pruning by setting constants like max depth, mean sample split, and mean sample sleeve. We control the growth of the tree during training. This ensures that the tree does not become overly complex and fits to the noise in the data. The logic is similar, so the accuracy remains similar to the previous pruning technique. The tree is simpler. Yeah, let's visualize the tree again. As for the model evaluation, we will skip it for here, but here we calculate like accuracy score, confusion matrix, classification report, estimate probabilities. Yes, tree-based model can estimate probabilities by calculating the proportion of samples of each class in the leaf nodes. We'll take a look at the receiver operator characteristic, precision recall curve, and like last score distribution. But we'll take a look at this part a bit later, so it's outside of this scope, since we wanted to take a look at the trees themselves. As a conclusion, in this practical session, we have walked through how to build, tune, and evaluate a decision tree classifier using the breast cancer dataset. We have highlighted key concepts such as hyperparameter tuning, finding the optimal parameters that improve model performance, cross-validation, using multiple train test splits to validate model robustness, feature importance, understanding which features have the most impact on the model's predictions, which is crucial in understanding the problem domain, pruning techniques, simplifying the model to prevent overfitting and improve generalization, and advanced evaluation metrics. You will take a look at them in this notebook. It is beneficial to evaluate not only accuracy but other metrics as well. Decision trees are not only easy to visualize but also provide valuable interpretability, which is often crucial in fields like healthcare, where understanding why a model made a certain decision is just as important as the decision itself. Feel free to revisit any of the steps in more detail, and do not forget to practice by modifying the code and experimenting with different parameters. That's the best way to learn. Do not hesitate to reach out if you have any questions or need further clarification on any of the concepts. Welcome back. Let us continue. We are discussing logistic regression. Logistic regression is a parametric supervised algorithm that classifies data points by estimating the probability that a given input belongs to a specific class. It does this by fitting linear boundary based on a logistic function, separating the classes by predicting a probability threshold. Let us take a look at the logistic regression. So logistic regression is a linear classifier used for binary outcomes, and it's modeling the probability that a given output belongs to a certain class. So there is a mathematical description of it, but what we should take into account is the cost function. So it's basically the function that calculates the errors. And cost function here is logistic loss, and like it is really useful for the binary classification tasks. Logistic regression uses logistic sigmoid function to model the probability of binary outcomes. It transforms linear combination of features to probabilities between 0 and 1, enabling classification of outcomes. The model is best suited for linearly separable data and uses a single interpretable decision boundary. Logistic regression assumes linear separability and benefits from scaled, non-correlated features to ensure reliable and interpretable coefficients. Logistic regression is computationally efficient for moderate-sized datasets with training complexity scaling linearly with the data size. Optimization algorithms like gradient descent make it feasible for large datasets, while regularization helps control overfitting in high dimensions. Logistic regression is known for its interpretability, making it easy to understand how each feature affects the outcome. Interpretable coefficients, so each feature has a coefficient, Wj, that indicates its impact on the log odds of the outcome. A positive coefficient increases the probability of a positive class, while a negative decreases it. By applying exponent to the coefficients, we get odds ratio, which tell us how much the likelihood of the outcome changes with 1 unit increase in the feature. Logistic regression produces probability estimates for each class, which allows us to set flexible decision thresholds based on specific application needs. And the model creates a linear decision boundary, making it straightforward to visualize and interpret the separation between classes. Combination of interpretability, probability estimates, and clear decision boundary makes logistic regression a powerful and transparent model for many classification tasks. While logistic regression is a popular and interpretable model, it does have limitations. For instance, limited binary classification. Logistic regression is naturally suited for binary outcomes. For multi-class problems, we need to adapt to it using methods like one versus rest and softmax regression. And this model assumes that classes are linearly separable, meaning it creates straight line or hyperplane boundary. This can limit its effectiveness with complex data patterns. Outliers can heavily impact the decision boundary, especially in smaller datasets, leading to less reliable predictions. And logistic regression may struggle with imbalanced datasets where one class dominates, as it tends to predict the majority class more often. And when the features are highly correlated, the coefficients become unstable and hard to interpret, affecting the model's reliability. So, what about strengths and applications of logistic regression? For the pros, it is interpretable. Coefficients provide direct insights into feature importance. It provides probability estimates, which are useful for decision-making thresholds, and it is computationally efficient, fast to train, and easy to implement for large datasets with low feature counts. As for the applications, logistic regression is popular in the fields where interpretability matters, like credit scoring, medical data, and customer churn predictions, for instance. Let us have some coding and take a look at the logistic regression. Hello everybody! Today we are going to work through a hands-on session using the Logistic Regression classifier. We'll be using the breast cancer dataset from scikit-learn, which is a well-known dataset for binary classification. This lecture will guide you step by step through implementing logistic regression model, understanding its nuances, and exploring advanced variations to achieve optimal results. Let's dive right in. And we start with imports. So we import models from scikit-learn and models from stat models and load the data set, since our data set is basically the numerical values. We do not need to convert anything to from one type to another one. So let's take a look at the data set and the samples, and we have target classes, and the dataset is relatively balanced, making it suitable for binary classification without imbalance concerns. Proper preprocessing is crucial for logistic regression to ensure that features contribute equally to the model. We will need to split the data. So the breast cancer dataset includes 30 numerical features that describe the characteristic of a cell nuclei. The target is 0 and 1, and this is a straightforward binary classification problem. Logistic regression benefits from scaling, especially when regularization is applied. So we will apply feature scaling. Logistic regression actually is highly sensitive to the scales, and we use scaling, and we will need to check the correlation. So the correlations here are giving us the insight that there are some features that are highly correlated between each other. We will need to remove them. So there is our function to remove them. But what we really need to keep in mind is that we check everything in train and then apply it in test so as to avoid leakage. And as here, so we started analyzing correlations on train and then just applied the reducing on test. As you can see here, this is the previous matrix, this is the new one. And again, we scaled the data, we scaled the train, and then applied scaling to test. And here we can start with the basic logistic regression classifier. Model training, well, the model is trained on the standardized data set, then evaluation, predictions are made on the test set, and accuracy is calculated to give an overview of model performance. Confusion matrix and classification report are created to understand the model's performance in detail, identifying how well it predicts zeros and ones. So the confusion matrix provides a visual representation of true positive, false positive, true negative, and false negative, which helps in understanding model errors. The classification report provides precision recall F1 score for each class. Precision measures how many of the predicted positive cases are actually positive. Recall or sensitivity measures how many of the actual positive cases were correctly predicted by the model. F1 score, it's the harmonic mean of precision and recall, providing a balanced metric when dealing with imbalanced classes. So this is the base model. The accuracy of the base model is 0.92. Let us find the best fitting parameters. We will use the hyperparameter tuning and grid search cross-validation to find the optimal values. And our parameter grid, we test different values of C, like regularization strengths, and the types of regularization penalties. Regularization helps prevent overfitting by penalizing overly complex models. By evaluating different models through cross-validation, we identify the parameter values that provide the highest cross-validation accuracy. Cross-validation ensures the model performance is consistent across different subsets of the data. And once the best parameters are found, we retrain the model and observe improved performance. As we can see here, there are some warnings, but overall, we identified the best cross-validation accuracy is almost 100, it's 0.98. Test accuracy with these optimal parameters are a bit lower, but we can validate using the cross-validation, and it is 0.97. Choosing the right regularization is important, and it plays a crucial role in the bias variance trade-off. A smaller C value applies stronger penalties, resulting in higher bias but lower variance, which may prevent overfitting. A larger C reduces the penalty, potentially leading to overfitting by allowing large coefficients. Let's take a look at some advanced regression models. We will explore L1 regularization. It's less so. It encourages sparsity in the model, which means some features coefficients are forced to zero, effectively removing them from the model. This can be beneficial for feature selection. And elastic net regularization is a combination of L1 and L2 penalties that balance between feature selection and coefficient shrinkage as well L2. These techniques help prevent overfitting and make the model more generalizable by controlling how complex it can become. So yeah, here's the feature selection, L1 regularization. We applied it using the cross-validation, and we achieved like the best cross-validation accuracy as 0.898, and we applied elastic net regularization. What is interesting is that test accuracy is a bit higher with elastic net, and elastic net best cross-validation is 0.97. Here is 0.898, but the test accuracy is a bit lower. So this is how we do it. Also, we need to mention that logistic regression can operate with a multinomial option, meaning it can solve multiclass, not only binary classification. But since here we do have only two outputs, like 0 or 1, the overall, it won't make any changes for us here. Model evaluation, we will skip it for now, but this covers evaluation beyond accuracy. It's all the things around, like receiver operator characteristic curve, area under the curve. Model evaluation covers evaluation beyond just accuracy. We will cover this topic during the separate session, but here you will have this notebook and everything is already implemented, so you'll be able to take a look and review everything. And logistic regression estimates probabilities by design, and that can be used for various evaluation metrics. So we'll skip this part, and we'll also skip the optimal threshold definition, all the statistics. What is interesting, logistic regression can be used from the stat models, and the stat models are pretty useful when you need to have something that is more statistically accurate. So you will have all the estimations of all the coefficients, confidence intervals, significance of features. And yeah, so this is really useful if you need to dive into the model. So it should be adjusted. I don't know why the accuracy is so low, but that requires review. And the feature importance for logistic regression, it is really interesting. So which features contribute to the most to our model is vital. And coefficient magnitudes in logistic regression, the magnitude of the coefficient tells us about the importance of features. We can visualize these coefficients to see which features have the most influence. The bigger it is, the better, and it has like positive or negative sign. So it's like helps to improve or helps to move to 0, helps to move to 1. And also permutation importance, it can measure the increase in the model error when a single feature's value is randomly shuffled. And this gives us an intuitive understanding of how much each feature matters to the overall model performance. And of course, we can use p-values and coefficients from the stat models. Yeah, we can take a look at the different features. Yeah. Permutation importance, as I mentioned. Yeah, here is also. You'll be able to just review all this on your own. In this practical session, we reviewed the logistic regression classifier using the breast cancer dataset, and we covered data loading and preprocessing, including scaling, which is crucial for logistic regression, model implementation and hyperparameter tuning, finding the optimal regularization parameter C, advanced variations of logistic regression, different regularization techniques to improve the model performance, model evaluation metrics. You'll be able to review it, and we have a separate session for this. Statistical insights that you can get with stat models, like interpreting coefficients, p-values, understanding the statistical significance of features. And feature importance itself, so using coefficients, permutation importance to understand which features influence the model the most. Logistic regression is a simple yet powerful algorithm that provides a good foundation for understanding more complex machine learning concepts. It emphasized the importance of data preprocessing, hyperparameter tuning, and interpretability. Moreover, it highlights the importance of carefully choosing the right evaluation metrics and decision thresholds, particularly in sensitive applications like healthcare. Feel free to explore by experimenting with different parameter settings and variations to gain a deeper understanding of the algorithm. And remember that practice is the key to mastering these concepts. And the more you experiment, the more insights you'll gain. And if you have any questions or would like to explore any of the steps further, don't hesitate to ask. Keep practicing and happy learning. Hello and welcome back. Let us continue. Support vector machines is a classification algorithm that finds the optimal separating hyperplane, maximizing the margin between classes. With kernels, it can handle complex nonlinear data, making it widely applicable across diverse fields. This graph provides a visual interpretation of support vector classifier with linear decision boundary. So solid line here is decision boundary, the hyperplane that separates two classes. Margin are shown as dashed lines. Boundaries where support vector lie, maximizing the margin between classes. Support vectors, circled points, that's a critical data that influences the boundaries position. Support vector machine finds the optimal hyperplane that maximizes the margin between classes. It's robust and powerful for high-dimensional and nonlinear data, but requires careful tuning and can be computationally demanding. Naive Bayes predicts by calculating the probability for each class given the features and assigning the class with the highest probability. This process is efficient, especially in high-dimensional data. So the probability of class C given X is equal to the probability of X given class C times the probability of class C, all divided by the probability of X. And this is like the formula, like Bayes theorem formula. Using this formula, we can estimate the classes. Using the Bayes formula, you can calculate the posterior probabilities, and basically what you need to do is to recalculate those formulas each time you do something with your data. What about the model evaluation? Let us briefly discuss what should we do and how to verify that the model actually brings value and the model is good. Evaluating a model requires multiple metrics, each highlighting different aspects of performance. The confusion matrix provides a foundational view, while other metrics like recall, AUC give more deeper insights. And there are advanced tools, and I will show them, that assess the performance on imbalanced data or like probabilistic outputs. But here we can take a look at what we have. So it's from the confusion matrix, we have four numbers: true positive, false positive, true negative, false negative. True positive is correctly predicted positive classes, false negative incorrectly predicted negative classes. It's type 2 error. True negative, it's like correctly predicted negative class, and false positive is incorrectly predicted positive class. It's type 1 error. We can calculate all the rates based on this data. There are more sophisticated metrics or basic metrics compared to the previous ones. So it's accuracy, it's the ratio of correct predictions to total predictions. This will be misleading in the imbalanced data sets. Precision is the ratio of true positives to all predicted positives. It is useful in cases where the cost of false positive is high. Recall or sensitivity is the ratio of true positives to all actual positives. It is important when missing a positive has a high cost. F beta score is a weighted harmonic mean of precision and recall, with beta determining the balance. So F1 for beta 1 balances both equally. As for the advanced metrics, here we have ROC curve. It's a receiver operator characteristic curve. It shows the relationship between true positive rate and false positive rate at various threshold levels. The diagonal line represents a random classifier, while the curve above it indicates model performance. The area under curve or AUC is a single value summary of ROC curve. Here the ROC is 0.2, suggesting strong model performance. Gini coefficient calculates as 2 times AUC minus 1, provides an alternative measure of separability, often used in credit scoring and risk analysis. As for the precision recall curve on the right, this plot shows precision versus recall for different thresholds. It is particularly useful when dealing with imbalanced classes, where one class is much more common than the other one. High precision and recall indicate good performance in correctly identifying the positive class while minimizing false positives. Area under curve and Gini coefficient help assess overall model separability, especially in balanced datasets. The precision recall curve is essential for imbalanced datasets, highlighting the trade-off between capturing true positives and avoiding false positives. On this slide, we are focusing on two advanced metrics used for evaluating classification models, log loss and the class probability density plot. Logarithmic loss or log loss measures the accuracy of the model's probability predictions, penalizing it more for confident but incorrect predictions. This is particularly important in cases where probabilities themselves are crucial, such as medical diagnosis or risk assessment. The formula here shows how log loss calculates this penalty by comparing the actual values y to predicted probabilities y hat. The higher the log loss, the worse the model performance. By minimizing log loss, we're essentially encouraging the model to be confident only when it's correct. Class probability density plot shows the distributions of predicted probabilities for each class. It is useful for visualizing model confidence. If the probabilities for each class are well separated, it indicates that the model is confident in its classifications. However, if the distributions overlap significantly, it suggests the model is uncertain. For instance, here we see that class 1 predictions are clustered around high probabilities close to 1 and class 0 predictions are closer to 0, which reflects good separation and confidence. Let us have some coding and we will review some of the metrics, some of the estimations. Hello, firstly I would like to talk a little bit about the contingency table or confusion matrix. It is often used to break down a model's predictions into categories that help us understand not only its accuracy but also where it is making mistakes. Let us explore the four components in more detail. So those are the main components. The true positive. These are the instances where the model correctly predicts a positive case, or it has an actual value like a true class and the model successfully predicted this class. Example, a patient who truly has a disease is correctly diagnosed as having it. True positive contribute directly to evaluating how effective the model is at detecting actual cases. The metric recall depends heavily on the true positives. False positive, these occur when the model incorrectly predicts positive outcomes when the actual case is negative. False positive, it is sometimes called type 1 error. Example, a person without a disease being falsely diagnosed as having it. False positive can be problematic in healthcare. For example, a false positive might lead to unnecessary treatment, stress, and additional tests. The metric precision is influenced by the number of false positives. High precision means fewer false alarms. False negatives. False negatives happen when the model predicts a negative outcome for a case that is actually positive. It's type 2 error. Example, a patient who actually has a disease is incorrectly diagnosed as healthy. False negatives are often more serious than false positives, especially in fields like healthcare or fraud detection. Missing an actual positive can lead to serious consequences, like delayed treatment. Recall is affected by false negatives, and a low recall means the model is missing too many actual positive cases. True negative, these are cases where the model correctly predicts a negative outcome for an actual negative case. Example, a healthy patient is correctly identified as healthy. Negative here means not the negative in our way, but like 0. So nothing happened, that means negative. True negatives help measure the model's ability to correctly dismiss false alarms, often evaluated using the metric specificity. So how to evaluate model using metrics? There are a lot of metrics. These 4 types of prediction allows us to calculate various evaluation metrics. The first one is accuracy. Accuracy is the ratio of correctly predicted instances, both positives and negatives, to the total number of instances. Accuracy is straightforward and easily to understand, but it can be misleading in imbalanced dataset. For example, if 95% of the data is negative, a model that always predicts negative would have 95% accuracy without being useful at all. It won't detect positive cases. Precision, or positive predictive value, measures how many of the predicted positive cases are actually true positives. Precision is crucial when the cost of false positives is high. For example, if we are predicting if a person is guilty of a crime, false accusations, false positives, have severe consequences. Recall, or sensitivity, or true positives rate measures how many of the actual positive cases the model correctly identified. Recall is critical when false negatives are more costly than false positives. In healthcare, for example, failing to identify a disease could lead to a lack of treatment. Specificity, or true negative rate, measures the proportion of actual negatives that are correctly identified. Specificity is important in situations where it is critical to avoid false positives. For instance, when screening for rare conditions, you don't want too many false positives, which could lead to unnecessary stress and expensive tests. F1 score. F1 score is the harmonic mean of precision and recall, providing a single metric that balances both. F1 score is useful when we need a balance between precision and recall, and it is particularly useful in imbalanced dataset. So why metrics are important? Well, different metrics are important depending on the context. In healthcare, we want high recall because missing a diagnosis can be life-threatening. And in fraud detection, high recall is important to catch as many fraud cases as possible, but too many false positives will make the system inefficient. And in spam detection, precision is key. If we mistakenly classify important emails as spam, users may dismiss critical information. We will review the model evaluation part of the KNN, but this remains the same for each model because model evaluation is actually the same. We're just evaluating the performance of the model. So in this code, we evaluate using various metrics and visualizations, which help us understand the performance of the model, and we estimate probabilities and use thresholds to balance different metrics. So let's break down step by step. First one is accuracy score, and we calculate it for the model, and this tells us the proportion of correctly predicted instances out of the total number of predictions. It is useful. It may be misleading for imbalanced dataset, but our dataset is not that misleading, and we have proved it during the data analysis and during the cross-validation. Confusion matrix, we've seen it. It visualizes using like heat map and helps us understand the number of true positives, true negatives, false positives, and false negatives. Classification report is a nice approach to have it in one place. Just a common support here is the number of actual occurrences in the class and the specified dataset. Since K and N returns only labels, we need to estimate the probabilities. So we can do this, and there is already made function for this in sklearn implementations of K and N. So how it calculates? It calculates the probability of each class by considering the proportion of neighbors belonging to each class. And we just can calculate the probabilities and then use it for other metrics. So receiver operator characteristic curve, or ROC curve. ROC curve shows us the trade-off between the true positive rate, TPR, and the false positive rate, FPR. The area under the curve shows like the classifier's performance. The closer to 1, the better. So 1 is ideal case, 0.5 is flip of a coin. The ROC helps us visualize how well the model discriminates between classes at different thresholds. Since to give true positive rate and false positive rate, we utilize thresholds, which is changing the threshold and getting this new data. What else we can do? Yeah, this is the distribution. This is how the ROC curve is calculated. True positive rates, the proportions. And as I mentioned, yeah, the AUC 0.5, it's a random classifier, and like 1 is perfect. Less than 0.5, it's worse than random. For some reason it discriminates the classes, or maybe you have flipped the labels. So when to use AUC ROC? It's balanced classes or a bit imbalanced classes, and by comparing classifiers you can do so. You can even calculate the ROC curve for different cross validations and like practical use cases, as I mentioned, medical diagnosis or fraud detection. The area under the curve represents the probability that the classifier will rank a randomly chosen positive instance higher than a randomly chosen negative instance. Class score distribution. We can plot kernel density estimation of the estimated propensity scores for each class to visualize how well the scores are separated. And here the picture. So the better separated these distributions are, the better the model's classification performance. It is that simple. And also it can help us estimate the threshold, since like we have the propensity score and it's actually the threshold where we label zeros and ones. What about precision recall curve and average precision? Precision recall curve helps visualize the trade-off between precision and recall for different thresholds, particularly useful for imbalanced datasets. And average precision gives summary metric that focuses on the model's ability to maintain high precision across all recall levels. And it is calculated like this. So higher AP, closer to 1, indicates that the classifier maintains a high level of precision even as recall increases, meaning it can capture positive instances without introducing too many false positives. Well, and lower is vice versa. The model struggles to balance. So average precision and like area under pair curve emphasize the model's performance on the positive class, which is crucial in imbalanced data set. And when to use it? For imbalanced data, of course, and for evaluating high recall systems. This will really help you. What about the threshold? So how do we estimate the threshold? Well, we can choose the optimal by moving, by modeling, by choosing the best F1 score that is possible, and we can also do so by finding the best point on the precision recall curve. There might be several points depending on how you balance it. Threshold analysis gives insights into where to draw the decision boundary, balancing different aspects of model performance. And there are a lot of metrics like UDENS, J statistics and other approaches for finding optimal ROC threshold. just choose the one and estimate everything. You can maximize specificity and sensitivity. Again, a lot of ways to calculate, and for some approaches, you have one option, for others like another one. So here, like f1 can be either 0.5 or 0.625. If we take back to the estimated propensity here, so 0.5 is right in the middle here, 0.6 somewhere here. Well, it depends. It depends on what type of data, what type of errors you would like to have in your data set. Just to sum up, the analysis combines different metrics and visualizations to fully understand the strengths and the weakness of the model. We reviewed like many metrics, the most popular ones like accuracy, precision, recall, two curves like ROC curve and precision recall curve, and area synthesis curve. And those are keys for understanding the overall performance. And threshold analysis can give you insights on the model and on the data. And this analysis, this evaluation, helps to ensure that the classifier performs effectively, especially in critical areas like correctly identifying positive instances while minimizing false positives and false negatives. Welcome back, and let's continue. So let us briefly discuss some challenges that happen for the classification tasks. Well, classification tasks face unique challenges from class imbalance and complex labeling to high-dimensional data and the need for model interpretability. Each of the challenges impacts the effectiveness of the classifier, and specific techniques can address them to improve model performance and transparency. For instance, like if we're talking about class imbalance, the most common technique is like over and under sampling and weighting schemes. You can apply weights to loss function. And classification is normally unbalanced in the real world, since in the real world you don't have like the perfect balance. Okay, it's time for the final notes. So the task of classification is about sorting data into categories. It's a key part of machine learning used to make decisions, whether predicting if an email is spam or identifying different customer types. This is classification. We covered some classifiers like Nearest Neighbours, decision trees, logistic regression. We had an overview of support vector machines and naive bias. Each model has its strengths, suited for specific types of data and goals. Choosing a model means balancing performance and interpretability, and logistic regression and decision tree are more transparent, while more complex models like SVMs or neural networks maybe often need extra tools to explain their performance and their predictions. We also discussed metrics that help measure model performance, from basic metrics like accuracy, precision, and recall to advanced metrics like AUC, precision recall curve, and log loss. These metrics provide insights into how well a model works in different situations. And yeah, we reviewed real-world challenges such as class imbalance, complex data, and interpretability. Thank you for joining this journey into classification. And remember, choosing the right model, evaluating it carefully, and understanding data challenges can lead to meaningful insights and better decisions. Make the most of each model's strengths, use the right metrics, and let data guide you to success. Keep exploring, stay curious, and keep building interesting things with the data. Thank you very much, and have a nice day.